The important word in this title, sorry, I'm speaking in English. The important word in this title is the word explores. This is an investigation, exploration, ideas, not a complete theory. It's a work in progress. It may not succeed. As you know, in the last 20, 30 years, there's been a lot of interaction between mathematics and physics, both ways. And this is part of that interaction from the point of view of a geometer, which is what I am. The physics is in the universe, I hope. Now, here I put three people's faces on the board to indicate some of the people who work in the area between mathematics and physics. On the left-hand side, I don't need to explain who this is. You recognize him. Then Roger Penrose, my colleague from Oxford in the middle. And on the right-hand side, Edward Witten, the great guru of string theory. All of them are very original, with very different points of view, and they cover a wide spectrum from mathematics on this side to physics on that side, with Penrose sitting somewhere in the middle. Now, let me quote for a little bit something I said 15 years ago at a conference in honor of Roger Penrose. And it's very pertinent in relation to these three people and in relationship to what I want to say later on. So let me start with this quotation. So I'll read it to you. As we all know, the fundamental problem that all physicists would like to solve is how to reconcile quantum theory with general relativity. In other words, how to produce a unified theory incorporating quantum gravity. There are many different approaches to this goal, and it is not, I hope, blasphemous to make comparisons with the way rival religions offer alternative approaches to God. To the protagonists, the various religions are mutually incompatible and at times distinctly hostile. To the skeptic, the different religious approaches simply cancel each other out, leaving a vacuum. At the other extreme, we have mystics who see underlying commonality in all religious experience and search for some fusion. As a side remark, we mathematicians might note, by analogy, that a combination of oscillatory functions can cancel themselves out, but yet leave a few delta functions at specific frequencies. If we turn now to the different approaches to quantum gravity, there are several rival philosophies or religions. The orthodox one is string theory and associated quantum field theory, and here the prophet is Edward Witten. We then have the twistor approach by Roger Penrose, and there's also a newer approach, that newer is from 1996, based on non-commutative geometry pioneered by Alain Connes. As skeptics, we have the hard-headed experimentalists who have little time for theories which deal with monstrously small or large quantities beyond the realm of measurement. On the other hand, there are mystics, among whom I include myself, hope for a synthesis which embraces aspects of all the rival theories. And as a mathematician, I would find it a pity if God had not found some use for all the beautiful ideas that have been put forward. I should say that in the intervening 15 years, there have been quite significant progress in producing links between the three different philosophies. Some steps towards a unification of ideas has taken place. Now, let me also quote from much further back, from Dirac. Paul Dirac, the great physicist, he said in Edinburgh in 1939, that's a long time ago, and he's making comments about quantum theory, and I would suggest, as a more hopeful-looking idea for getting an improved quantum theory, that one takes as basis the theory of functions of a complex variable. This branch of mathematics is of exceptional beauty, and further, the group of transformations in the complex plane is the same as the Lorentz group governing the space-time of restricted relativity. One is thus led to suspect the existence of a deep-lying connection between the theory of functions of a complex variable and the space-time of restricted relativity, the working out of which will be a difficult task for the future. Well, this is very much in the spirit of Roger Penrose's work, but in 1939, Roger Penrose was still in primary school. He didn't know about this. He had to wait, but Dirac said it first. Now, I'm going to talk about two different problems, which are not really very closely related, both new ideas which I'm putting forward as a mathematician for consideration in possible uses in physics. Now, the first one begins with the following fundamental questions. what is the small-scale nature of space, or space-time? First of all, at very, very small scales, things are experimentally inaccessible. It is impossible by any kind of physical apparatus to test things beyond a certain ultimate scale. It's impossible. And so this question arises, is the continual model we make of space and time still valid at such arbitrarily small scales? Or, alternatively, is space-time at very, very small scales not a continuum, but in some sense granular? Well, granular is a vague term indicating perhaps something between the discrete and the continuous. At small scales, the continuum may not be any longer a good model. Perhaps we need some new kind of model. Now, this idea, of course, is familiar to many physicists, and here is a quotation from a standard textbook of Bjorken and Drell, who wrote 2 volumes on quantum field theory. This is volume 2, Relativistic Quantum Fields. And they say in their introduction, the book is quite old, even if there is granularity at small distances, if we are to retain microcausality, the influence of one granule upon the next must be retarded. It must take a little time for the signal to move from one granule to the next, is what they say. And then they make the following comment. They say, we will ignore this possibility. Why? Well, we found out that ordinary differential equations, not retarded, are very successful in physics, and they seem to provide answers to all the questions we want to ask. There seems to be no reason to go into anything more complicated. And since the theory of such retarded equations is mathematically unknown, why should we bother to look into it? Well, the situation has now changed 15 years, 20 years later. There are problems in physics which are currently, present theory is not satisfactory for. I remind you only of the famous problem of the cosmological constant, so-called dark energy, which is very mysterious, very fundamental. The present theory has nothing to say about it. So there are mysterious problems which may need new ideas. And what I want to talk about here is that if we follow this line of looking at retarded equations, there is a way to reconcile those and to develop a reasonable mathematical theory. So it's not impossible to develop mathematical theory which retains some of the ideas in this statement here. So let me begin by just recalling very briefly what we mean by a retarded differential equation. Let's take the simplest example of a function of one variable, and we write out an equation which involves the derivative with respect to x, f prime of x, plus a term fk, a constant, times fx minus r. The important thing is that the evaluation of the function takes place not at the same point x, but at the point x minus a constant. R is thought of as a positive constant. This is the simplest kind of retarded differential equation. Now, this equation can be very easily solved, of course, by integration. But what you have to do to specify the initial data, unlike an ordinary differential equation where there's no r, you must give not the value of a function at one point, but the value of a function over an interval. In fact, the interval from 0 to r. If you specify the function arbitrarily in that interval, then by integration in successive steps, you can propagate it in one direction, and going backwards by differentiation, assuming you can differentiate arbitrarily many times, you can solve this equation. So equations like this can be solved, but the initial data is not value at one point, but is in fact a Hilbert space of functions. That is already suggestive of quantum mechanics. But secondly, you may have more difficult problems which involve not just equations which are retarded, but also equations which are advanced, where you replace not only minus r, but plus r. So I've written at the bottom an example here of an equation with plus r and a minus r. Philosophically, this is more difficult to understand. Easy to understand that if you know the past, you can predict the future, but here you have to know a bit of the past and a bit of the future to predict the present. So philosophically, it has some difficulties, but actually, the difficulties are not unlike those in quantum mechanics. In fact, in quantum mechanics, there is uncertainty principle. If you think of the uncertainty as being applying to instant of time, then a little bit of the past, a little bit of the future are in some sense uncertain. So the difficulties involved in mixed or shifted equations, we move both ways, are also reminiscent of quantum mechanics. So even at the very elementary level, questions of retarded equations suggest some new point of view is necessary. But now the question that fundamental question arises is that It's all very well to have a retarded equation in one variable. But what about if you go to space-time and you want to have a theory which is relativistically invariant? In relativity theory, there is no preferred time. And it's fundamental. We like a theory relativistically invariant. It's been very successful. We would not like to discard relativity. So how can we preserve relativity and yet, at the same time, introduce the idea of retarded or advanced equations? People will think this is impossible, that if you have down to small scales where you put in some discrete information, then you destroy all the continuous symmetry. That's why people don't like it. So let me explain that it's possible to preserve continuous symmetry while also introducing retardation. Now, the solution is simple. We remember that the differentiation in one variable is the infinitesimal generator of translation. In other words, formally, to take the function and move it backwards is the same as exponentiating this operator on the function. Now, if you want to therefore just define retardation in time in a relativistic situation, what you need is to have a first-order differential operator, which you would then exponentiate, and you want the operator to be relativistically invariant. Now, there is only one first-order differential operator which is relativistically invariant, and that was discovered by Dirac. The Dirac operator is exactly the solution to that problem. And what Dirac found was that this exists, essentially unique, and therefore if you could put the Dirac operator into the exponential, you have a notion of retardation which is relativistically invariant. It's a very beautiful solution. Of course, as Dirac discovered, you have to have spinors. This does not act on scalar functions, you have to act on spinors. But that's fine, we don't mind that. Spinors have been used by physicists ever since Dirac introduced them. But Dirac also discovered a very awkward problem, namely the Dirac operator acting on spinors has both positive and negative frequencies, which means that even if you write an equation like that down, when you replace this by the Dirac operator, besides having really some part of it is retarded, some part of it is advanced, depending whether you're acting on one kind of spinor or another kind of spinor. So automatically, the Dirac operator has to face up to both retarded and advanced things. This is the fundamental difficulty of quantum field theory, which is solved in the conventional framework by introducing the Fock space, which creates and annihilates particles, and is a very complicated mathematical and philosophical notion. But nevertheless, the Dirac operator does enable you to define a relativistically invariant operation of retardation. Now, you can ask, what does this mean to exponentiate the Dirac operator? What it means physically is quite simple. If you have any plane wave, any physically wave function in space-time, you can decompose it into Fourier components. Waves propagate in different directions. And in each direction, you can then retard that component in its own proper time. Then you integrate it up, come back, and then you've got the operator of the Dirac acting in all directions, and it's invariantly defined by going to the Fourier transform. So it makes perfectly good sense. Every wave is retarded in its own direction. There are different directions with different components, but you add them all up at the end. So it makes good sense to introduce this operator. So I wrote a short paper with a colleague who's a physicist, Greg Moore. And here's the title page. And what we simply took this idea and wrote down the simplest kind of retarded Dirac equation we could think of, and to see what consequences there were. And there were some rather simple but significant formal consequences. And I want to just mention them, and then I will leave this and go to a different topic. Now, what we found was this following. You write down the Dirac operator, a very short symbolic notation here. You add to it a constant times the exponential of the Dirac operator with a coefficient minus r. So there are two constants in this operator, k and r. In the usual case, you put k equal to 0, you get the ordinary Dirac. Or if you put r equal to 0, this becomes a constant. But you want both non-zero. One thing you find very, very quickly if you follow this operator up is that the condition that some things should be real, physically significant, requires that the quantity r should be quantized. You want some component of the exponential function to vanish, e to the I, and therefore this r has to be quantized, which means it must be an integer multiple some fixed number. And then you think that this number should apply, the fixed number should be based on some fundamental elementary particle. Depending which particle you take, you get different values for this constant. And if you take the neutrino, you get 10 to the minus 5 centimeters. If you take the electron, you get something considerably smaller. So you get a nice, interesting fact about this parameter r is quantized, integer multiple of fixed value. If you then apply this Dirac operator not just to the usual Dirac equation, but you apply, if you square it, if in other words you take spinors times spinors to give you differential forms, and you go towards the Einstein equation, which governs on one forms, then you find another formal fact which comes out, which is that the constant k divided by Planck's constant squared should be the cosmological constant, and gives you scales of this extremely small size is what consistent with the experiment. And the numbers k and r are in fact related with Planck's constant by a certain dimensionless constant. So you get some very interesting, elementary, formal, and not entirely clear what they mean, results from this formulation. And just by following your nose is the only thing you can do, only one way to introduce relativistically retarded equations. And so why not? We don't need to destroy the beauty of the physics. We preserve the nice relativity theory, and we can follow it up in terms of the physical consequences. This is the first step. I don't entirely understand what we're doing here, but the formulas are quite clear, and there's some interesting consequences, and nothing contradicts experimental data. Now, I mentioned here a question at the bottom, and very relevant because I'm here in the Collège de France, and that is this. Alain Connes, in his theory of non-commutative geometry, has a very interesting application to physics. In his model, you take space-time, ordinary space-time, and then you take two copies, a very small distance apart. So imagine this universe has a kind of parallel one at a very small scale, very near, so small you don't notice the difference. And then he worked out the mathematics of this, the non-commutative framework, and he got very good, he was able to reproduce the so-called standard model of basic physics rather surprisingly well out of some simple ideas from non-commutative geometry. Well, the question I've posed here is the shifted Dirac operator, which compares the value at one point with the value at a very nearby point, is it somehow related to Connes' idea of having two copies of the space-time? These are both mathematical ideas, and they both have relation to physics with different consequences. It's not inconceivable that they have some direct link between them. Naively speaking, if you imagine you have two parallel copies of the universe, you might send a signal. One copy, it bounced off the other one, comes back, like the things off the ionosphere and up the stratosphere, and this signal will be delayed because of the time it takes to go there and backwards. So you can imagine delayed signals, but you also do it the other way around. So you can see some way in which two parallel copies might produce retarded equations. I don't know. I came here to discuss it with Alain Connes. We will discuss it over lunch. Perhaps after lunch we will have the solution. And then you can talk about it next week. So, okay, that's the first topic I wanted to discuss. So you see, it's very formal, but it comes from the point of view, my philosophy here is that I want to follow geometry in its natural way. I don't want to do anything artificial. I want to do what is natural to a geometer. And using the Dirac operator, using the spinors, all these are totally natural operations in geometry. And then you see what relationship they have with physics, what the physical implications are, see where you can go. And you start. After that, you have lots and lots of things to do. Now, the second part of this talk is different development of the same fundamental idea. I want to use geometry as a way of trying to do all physics in a different sort of way. So now I'm going to start with reminding you of the two fundamental dichotomy in physics in the 20th century. The two greatest physicists, the first half of the 20th century, were Niels Bohr, who was the great champion of quantum mechanics, and Albert Einstein, who was the great champion of general relativity. And Einstein thought in terms of geometry, and Bohr thought in terms of quantum mechanics, which is really in terms of algebra, Heisenberg commutation relations, and spectral theory, and so on. So this is the two different aspects of physics or geometry. One is spectral, concerned with eigenvalues of operators and so on, The other is concerned with the geometry, the curvature, things like that. And in ordinary mathematical terms, these are sort of dual points of view about studying some geometrical object. In physics, they reflect the quantum mechanics, the relativity divide. And this big debate between Einstein and Bohr, which went on for decades, most people in the community think Bohr won the argument. Einstein retreated. Well, actually, he never gave in, Einstein. He said, well, I believe quantum mechanics is very good, it gives you very good results, but I don't think it's the ultimate truth. The ultimate truth lies buried deeper, and we want to find it. And he kept on looking for it all his life, and he didn't find it, but subsequent developments has suggested that he had something on his side. Now, the first step beyond quantum mechanics and relativity is to go to look at electromagnetism. Gravitation is the oldest force we know, going back to Newton. Electromagnetism is also old and also very important in everyday life. And it was discovered quite early on, after Einstein's theory of relativity, how to incorporate electromagnetism into geometry. This idea is fundamentally due to Hermann Weyl, but was also adopted by physicists, Klein, in a different formulation. And the idea is this, that electromagnetism is modern language of physics concerned with U1 gauge theory, the circle group. The potential is of the connection of a U1 theory. The curvature is the force. And this point of view of Weyl, Klein, is that this extra circle of the fiber bundle over space-time, should be incorporated into space-time and made part of a 5-dimensional space-time. If you take a 5-dimensional space-time divided by circles, and you write down Einstein equations in 5 dimensions, lo and behold, you recover the Einstein equations in 4 dimensions plus Maxwell's equations. So it's a very beautiful unification of electromagnetic theory and gravitation. Now, inside this theory, there are some refinements. If you have a 5-dimensional space which has an action of a circle, symmetry, but it's not a vibration, what can happen is that the circle can have some fixed points. The circles degenerate, they change their length and shrink to one point. The interpretation of this fixed point of the circle action is what's called a magnetic monopole. If you go down from the 5-dimensional space back down to 4-dimensional space-time, the fixed point appears there as the source of magnetism, what's called a monopole. A monopole is something that doesn't physically usually exist in the lab, but mathematically, in Maxwell's equations, it can exist. So a magnetic monopole in this geometry is just a fixed point of the circle action. And this, fundamentally, was an idea used by Dirac when he gave the first explanation of the fact that the electric charges of particles are quantized. Every particle in nature has an electric charge which is an integer multiple, either 0, positive or negative, of the charge of the electron. And his argument is essentially a topological argument, and in modern terminology, he identified the electric charge with what's called the first Chern class of the circle bundle, where you cut out the fixed point. Around that point, there is a standard line bundle. That line bundle has a Chern class, which is a class on the two spheres surrounding the pole, and that is identified with some appropriate units with the with the magnetic charge. So, topology appears here at a very important level, linking the quantization of magnetic charge and electric charge go together. What you get from this argument is that the electric charge is quantized. And if you think about it from the geometrical point of view, the circle is the most fundamental object in mathematics in many ways. It appears twice here. First, in quantum theory, you look at the representations of the circle, and that gives you states. Quantum mechanics, on the hand, you look at the topology, that gives you the topological charge. In topological language, it's the duality between homology and cohomology. All very simple for a circle, more complicated for more complicated groups. But this fundamental level, the first Chern class appears to explain the quantization of electric charge. This is a very famous idea of Dirac, which has persisted and been generalized in modern theory to more complicated situations. Now, once you go beyond electromagnetism and gravitation, the fundamental problem is what is the nature of matter. Einstein said in his equations he has a beautiful left-hand side which describes the Ricci tensor curvature of space-time, and the right-hand side is, he said, a mess. It is what is produced by matter. And he didn't know what it was, so he had a beautiful equation on the left and an ugly thing on the right-hand side. And he was really searching for some beauty, something to replace that ugly theory on the right-hand side to get a combined theory of matter and structure of matter and gravity. Now, the theories that are developed in the second half of the 20th century by physicists were exactly how to handle matter. And these turned out, surprisingly, to involve non-abelian gauge theories. These are the generalizations of the U1 gauge theory of electromagnetism to non-abelian Lie groups like SU2 and SU3. And these are the framework in which all present-day elementary particle physics is conducted. So to that extent, Einstein was right. These are geometrical objects given by curvature of bundles, and they describe the fields that are relevant to matter. On the other hand, the theory is still a quantum theory. So we have a compromise between Bohr and Einstein. This theory is really geometrical, but also quantum mechanical. The Penrose twistor theory is, I put it on the right-hand side, it lives in this general world, but has a different flavor. Alain Connes' non-cubic geometry is an explanation, as I told you, of the standard model. The standard model is a theory, gauge theory involving the big group, U1, SU2, and SU3, which correspond to different fields, different particles, and a very complicated interaction term, which is what Connes was trying to explain. So present-day theory of matter is built along these lines, partly geometrical, partly quantum mechanical. But still, at this stage, they're not really incorporated with gravity and this theory don't really fit very well together. Now, there is an approach to matter, or to study of the nuclear matter, which is quite much older than these theories, which is what I want to talk about now. It was introduced by a mathematician called Sturm, and he's what gives us a model of the nucleus. This model of the nucleus is a classical model. It ignores quantum mechanics. And in the first level, it also thinks it ignores time. It concerns itself with static nuclei. And later on, you study the dynamics. And Sturm's model was a very interesting, very idea far in advance of its time. At the time, it was ignored. Subsequently, people came back and said, aha, this is interesting. It was an example of solitons. It has a relationship with the standard model. And people have taken it more seriously. And although it's not a quantum mechanical theory, it had actually been put to use by people trying to understand the actual structure and nature of different kinds of nuclei. Because although even if you have a general theory, the standard model, the theory is so complicated that in trying to get useful information out of it, simple questions in nuclear physics is very, very difficult indeed. So it's very useful to have simpler models which you can use for those purposes. So for a variety of reasons, this Sturm model is interesting. Now, what is the Sturm model? It concerned itself with three-dimensional space. Time has been ignored for the moment. And we take three functions, or rather map from R3 into the group SU2. And you assume that asymptotically this function tends to the unit element of the group as x goes to infinity, which means that you can compactify the function to have values on the three-dimensional sphere, and its target space is also the three-dimensional sphere, the group SU2. So it has a topological degree. And Sturm's idea was the topological degree is identified with the baryon number of the nucleus. The baryon number is the number of protons and neutrons together. This theory of Sturm does not distinguish between protons and neutrons. It does not allow for electric charge, which is the distinction, but it counts the baryon number and gives it a topological interpretation. Now notice that the Dirac gave topological interpretation to electric charge. Electric charge is ignored here. So you have two different bits of topology. The first Chern class gave electric charge. Here we have the second. We have something in degree 3, which is really related to the second Chern class. And this was Sturm's idea, that the topology should somehow lie at the basis of the structure of matter, should be counting the number of baryons. And Sturm wrote down an energy functional whose minimum would give the stable configurations of nuclei. A single nucleus would correspond to one proton or one neutron, would correspond to a spherically symmetric solution of the corresponding Euler-Lagrange equations. Skyrmions have been studied because they're a quite explicit mathematical problem, although there are no explicit solutions known. Even for this one skyrmion, it has to be done by writing down an ordinary differential equation, applying numerical methods, and finding some very good approximation. So the higher ones are even more difficult. But they have been studied systematically for increasing numbers of baryons by Manton, physicist in Cambridge, and many students, and I've been involved in some collaborations with them, and a lot of work has gone into the skyrmion. By the way, it's very convenient to have the right kind of name if you want a particle named after you. If you're called bose, you get bosons. If you're called fermi, you get fermions. If you're called skyrm, you get skyrmions. Atiyah is unfortunately not very suitable for adjectivization. Get the right name and you become famous. Now, I mentioned the word solitons. Solitons are one of the most interesting things to emerge in mathematics, mathematical physics, applied mathematics in the last 50 years. They cover a wide range of activities. You find articles about them in the journals of electrical engineering and in connection with Lie groups and pure mathematics. And they cover a wide range of examples. And what they are, fundamentally, are solutions of certain nonlinear partial differential equations which get concentrated near some points. They look like particles. They behave like particles. They interact like colliding particles with some complicated interaction. And they, therefore, can be thought of as models for different kinds of particles. And the skyrmion is really an example of a soliton model for the nucleus. But mathematicians have learned that solitons are also important in pure mathematics. And if you take the Yang-Mills instantons, these are the instantons introduced in physics for the SU2 bundles. You write down the curvature, integral of the curvature squared, that gives you a functional, and you look for the minima and so on. And the solutions of these were called instantons because they had to do with an instant in space-time. Admittedly, time in this model is imaginary time. You're dealing with four-dimensional Euclidean space. And as you probably know, these instantons were used by Simon Donaldson to spectacular effect in discovering and exploring totally new phenomena in four-dimensional geometry, which came out of physics by background, but mathematically they're well defined. And these are remarkable phenomena in four dimensions which have been studied. So solitons have a wide range of applications, and they are related to Lie groups and all sorts of things. Sometimes the soliton equations are soluble by some rather explicit methods, what are called integrable systems. And the Yang-Mills equations are examples of that kind, and the techniques of solving them really go back to Roger Penrose's twist theories. So there are, this model has explicit solutions. The Skyrm model does not have explicit solutions. But there are sometimes relationships between them. And what Manton and I found some years ago was a very simple way of trying to use information about instantons to give you information about skyrmions. And the idea is very naive. You take your four-dimensional space and you think of it as R1 times R3, and then you think you have in four-dimensional space, you think you have an SU2 gauge field, which means mathematically you have a SU2 bundle with a connection and a curvature, and you put some asymptotic conditions so it decays at infinity, and then the strength of this curvature is, so to speak, describes the instanton when you solve the equations. And then if you have such a field, then you take parallel transport along this direction, and because the asymptotic conditions at infinity are standardized, this really gives you an element of the gauge group. The group map R3 into the group. And that's exactly what a Skyrm field is. So by just parallel transport of one extra dimension, you go from a bundle with connection to a map into the group. This is very familiar to topologists. It's going from the group to the classifying space. And that will relate, for example, H3 of the group to H4 of the classifying space. So it's no surprise to find that the instanton number, which is really the second Chern class, gets converted into the Skyrm number, which is interpreted by Skyrm as the baryon number. So here I alluded to that a few minutes ago. I said the first Chern class is related to electromagnetic charge. The second Chern class is related in the Skirm model to the baryon number, the two most important components of nuclear physics. Even though the Skirm field ignores charge, only picks up this part of it. Somewhere else, U1 will give you electric charge. Anyway, this is a construction which Manson and I did, and it turned out to be quite useful. You can start off with some known instance on fields, you can construct some Skirm fields, and then you try to improve on those. In this way, you're able to construct some rather explicit solutions of the Skirmion equations. And these can then be tested out. You get models for nuclei with certain small nucleus numbers, up to about 10, 12, and you find some remarkable results in terms of the configuration shape of these nuclei. That's been around some time. Now let me move to something, my new idea. The idea is this. There are two kinds of geometry involved here. One is the geometry of bundles and connections and curvature. And the other is the geometry of a manifold, the Riemannian manifold. Now, both of them involve curvature. The Riemannian manifold has the curvature of its own tangent bundle, and then you can auxiliarily put an arbitrary other bundle and look at the curvature of that. Now, if you have a little piece of a manifold, it looks like Euclidean space. If over that you have some bundle with a connection which is very highly concentrated in that region, you don't really know whether, if you go far away, your space is R4, just with some asymptotic decay to infinity, or it's a little piece of a four-dimensional manifold with some complicated topology far away. They're, as far as you're concerned, more or less the same thing. And so this idea here is that I want to go not from gauge fields like this. I want to go back to geometry. By geometry, I mean a Riemannian manifold. And the advantage of a Riemannian manifold is that you have much less choice in what kind of groups you choose. If you have a gauge group, you can take any group you like, SU2, SU3, SU4, SU5, and physicists have played around with these, and exceptional groups. So there's almost too much choice. If you start off with four-dimensional manifolds, the choice is limited to the groups that occur in the geometry of 4 dimensions. And let me remind you what those are. If you're dealing with, so actually, as usual, something happens with, things got in the wrong order. If you have a general manifold with Riemannian metric, then the structure group of the tangent bundle is the SO4. If you go around a path and come back with parallel transport, you get a 4-dimensional rotation of the tangent space. And in 4 dimensions, group SO4 is locally double covering isomorphic to 2 copies of SU2. And so you find naturally inside 4 dimensions the group SU2 coming out of the internal geometry. The SU2 are really the groups that act on spinors. Just as spinors are buried deeply inside a manifold, SU2 is part of the geometry of the manifold. It doesn't have to be produced by hand from outside. I think I prefer this. A Kähler manifold is a special kind of manifold in which the holonomy, one of these SU2s, is broken down to a U1. That gives the complex structure and the Kähler metric. And a special class, even further, more special, is when you have what's called a hyperkähler manifold, where the second group becomes trivialized completely. The only holonomy is in SU2, and these are called hyperkähler because they're Kähler for many choices of the other factor. Now, in a manifold like this, in a hyperkähler manifold, hyperkähler manifold, one of the spin bundles is trivial, this one here, the other one is non-trivial. So you have 2 bundles, and you have 2 SU2s, and you can choose one rather than the other one. Now I think I'll go backwards. So now, this is my second part of my lecture. I want to put forward the following idea. The geometrical model of matter, and I use the word matter here rather more generally the nucleus, should be given by an oriented Riemannian 4 manifold. No gauge group, just geometry. Important, it should be oriented, and it should be Riemannian. And manifold should be either compact or complete. Now this manifold should be fibered by circles. So this looks like if you have a Kaluza-Klein 5-dimensional space and you throw away the time coordinate, you will get a 4-dimensional Riemannian manifold fibered by circles. That's the kind of manifold I have in mind. with two differences. First of all, I only require the circle vibration to exist asymptotically. Asymptotically means far away from the central core of the matter, just like for the monopole. But secondly, I want to invert the roles of electricity and magnetism. Electricity and magnetism arise in Maxwell's equations in a very symmetrical manner. And at least formally, you can switch their roles. So I want to interpret what was previously magnetism as electricity and vice versa. Now, the first thing is the role of orientation. The manifold is oriented, and if you reverse the orientation, the idea is that matter gets converted into antimatter. As we know, the universe has matter, is antimatter. We have protons, antiprotons, electrons, positrons. Every particle has an antiparticle. In this model, it's the same geometry with the opposite orientation. Very simple. So that's the first observation. Now, the second thing is to look at conformal geometry. Conformal geometry, two Riemannian manifolds are conformally equivalent if their metrics differ by multiplication by some non-zero function, which changes the scale at every point. In the case of surfaces, we know that conformal geometry leads you to complex and analytic geometry. So conformal geometry in 4 dimensions is particularly interesting. Now, in general, if you have manifold with a Riemannian metric, then the Riemannian curvature, a complicated term with lots of indices I won't write down, can be broken up into 2 parts. The so-called Ricci tensor and the Weil tensor. Now, the Ricci part is a symmetric 2x2 object. It has a trace, which is called the scalar curvature, and it's the traceless part, when you remove the trace. In 2 dimensions, the scalar curvature is the only invariant of geometry. In 3 dimensions, the only invariant of geometry is the Ricci tensor. But in 4 dimensions, you already have an independent part, the Weil tensor. And this part is conformally invariant. This is not conformally invariant. Now, in 4 dimensions and above, the Weil tensor, this can be always true, but in 4 dimensions, something special happens. The Weil tensor breaks up into 2 parts, the self-dual part and the anti-self-dual part, because in dimension 4, 2 forms are dual to 2 forms, and the curvature is a 2 form. So you can decompose the Weil tensor into 2 parts. So in 4-dimensional geometry, conformal geometry, there are 2 invariant bits, and the manifold is said to be self-dual if 1/2 is easy as 0. So W minus is 0, we call it self-dual. If W plus is 0, we call it anti-self-dual. And changing the orientation interchanges those 2 roles. Okay? So once you've got the orientation fixed, you know which we're talking about. We want to talk about self-dual conformal for manifolds. And that's the class of manifolds which I want to put forward as models for matter. It's a very simple class, very fundamental in geometry, and I'll say more about them as we go along. Now, the first observation, so antimatter given by anti-self-dual. Now, these 4 manifolds, the conformally self-dual manifolds, are precisely the manifolds which Penrose's twistor theory applies. Now, I haven't said much about the theory except by allusions, but what Penrose's twistor theory does is he starts off with a manifold M, 4 dimensions, which is conformal structure and is self-dual. Over this, you construct a bundle of 2 spheres to get a 6-dimensional manifold, and then lo and behold, you discover that the 6-dimensional manifold has a canonical natural holomorphic structure as a complex 3-dimensional manifold. And all the geometry and the complex 3-dimensional manifold has an addition, an involution, which is anti-holomorphic, which is on each 2-sphere the antipodal map, and so it's like a real algebraic variety defined over the real numbers. It has a complex conjugation. And this entirely encodes the geometry of the 4 manifold. You can go backwards and forwards. It's equivalent. And this advantage of this is you can apply the theory of complex variables in 3 dimensions, sheaf cohomology groups, and all of that. This has been done very successfully. This is the way the instanton problems have been solved by going to twistor space and applying complex variable techniques, but in complex dimension 3, not what you might think of as dimension 2. The point about 4 real dimensions is it is, in fact, you can think of it as 2 complex dimensions, but there's no unique way of doing it. But if you introduce the 2-sphere, that encodes all the different ways of doing it, and when you go to 3 dimensions, there's total symmetry between the complex variables of the space, which is, you think of as two complex, and the complex variable of the fiber, which you think of as a two-sphere. They're on equal footing. For example, if you start with your four-manifold being the four-sphere with the round metric, then the twistor space is complex Betti 3 space, all its symmetries. So it's a very beautiful theory, and I haven't got time to develop it, but this is Penrose's contribution. And so if I'm taking the self-dual four manifolds as my models of matter, I have the full power of Penrose's twistor theory at my disposal. I can use complex variable techniques and the very sophisticated ones as well. Now, one of the properties of these self-dual manifolds is they can be glued together. If you have two self-dual four manifolds, then you can cut little holes, put them together, and find on the resulting glued manifold a self-dual conformal structure. You can do this, but not always. Sometimes there is an obstruction, and when there is an obstruction which is not zero, you can't do it. So you can do it sometimes, but not always. This is related to the Donaldson theory in four dimensions, which shows that there are some subtleties in four dimensions, and these subtleties appear in the nature of these obstructions. So we're getting here into the heart of Donaldson theory. And one of the reasons I like this approach is, in fact, the Donaldson theory is a very rich theory of four-dimensional Riemannian geometry, which emerged out of physics indirectly and was interpreted in terms of physics by Witten and people like that. But their interpretation is slightly, how shall I put it, unnatural to me. Their interpretation involves changing certain things. For example, they start off with Minkowski space signature, then they do what they call a Wick rotation. You put in an eye, you change it to Riemannian geometry. It's not entirely natural. It's certainly not natural for the curves manifold. They also do what they call twists. If you've got a four-dimensional manifold, locally it has two SU2s inside it, in the tangent space. If you put on top of that a gauge theory with an SU2, you have a third SU2. And now sometimes you can mix these together. And these give rise to twisted theories, and Witten and people have exposited these twisted theories to link Donaldson theory to physics. It's all rather convoluted in my view. My approach is more naive. I work only with Riemannian geometry. I've thrown away the time variable for the moment. I have four dimensions. I have no need of any twists. The geometrical models are as they come, and it seems totally natural geometrically. And we have this theory of Penrose, which enables us to glue things together. By the way, this gluing process has been carried out by Donaldson and others. It uses the Penrose twistor theory, because you take each of your manifolds, which is self-dual, has a complex twistor space. You take the two complex twistor spaces, a point in the four-dimensional manifold corresponds to a sort of complex line in the twistor space, and you take a neighborhood of these two complex lines, you glue them together in the form of complex analysis. And this is the deformation theory of complex varieties, which is very well developed. So using rather advanced techniques in complex analysis, you can glue them together, and you can find sometimes an obstruction in some cohomology group. Sometimes there is no obstruction, and so this is a powerful way. And so these behave in many ways like Riemann surfaces, but they're more subtle. They have some deeper properties, which is hopefully related to deeper properties of matter you're trying to model. Now, there are also complex moduli spaces. When you have a manifold with a self-dual structure, it can vary, the parameters can vary, and you have moduli, because the corresponding twistor space is a complex manifold. That complex manifold will have complex moduli. So the moduli spaces are naturally complex, and you can move around in them, and if you move around, you're deforming or changing the self-dual four manifold from which you started. So this theory of moduli spaces allows for not only models of static matter, but for deformations of the matter, and also for potentially breaking up and fusing. In other words, what you would call interactions, fission and fusion. So the geometry has within it the machinery and the techniques for handling complicated interactions and deformation, all in terms, entirely natural geometrical terms. I'm not inventing anything. This is standard complex analysis plus Penrose's idea applied to differential geometry. So it's a very natural, not forced in any way, and you can carry it through. Now, that's the idea. Now, first of all, if you're talking about matter, you have to describe what are the basic building blocks. Now, the basic building blocks of matter are protons and neutrons on the one hand. On the other hand, electrons and neutrinos. They have different labels in physics. The protons and neutrons are called baryons, and the electrons and neutrinos are called leptons. Don't worry about the terminology. So here I've got the 4 building blocks, types, and the idea is that the difference between these ones and these ones is that the baryons have a non-trivial second homology group. And the leptons don't have any interesting second homology group. On the other hand, there's another way you can distinguish these 4 objects according to whether they're charged or not charged. Now, the proton and the electron have charges. This is plus charge, this is negative charge. The neutron and the neutrino, as the name suggests, are neutral. They have no charge. So the distinction here I make is that the charged particle is a non-compact manifold, and its topology to infinity has these circle bundles we give first Chern classes, which tells you how much electric charge is trying to escape from the manifold. The neutral particles are compact manifolds. They have no infinity. There's nowhere for the charge to go. So in a way, very simple alternative models. Compact, non-compact, and two-dimensional homology somehow plays a role for counting baryon number. All very natural from the point of view of geometry. Now, let's look at the first example, lepton. Now, these are the easiest ones. Originally, when I started this game, I was trying to model the nucleus, like the skyrmion. But as I got a little further along, I realized that the models I was doing also dealt with leptons. So why not? In fact, the electron, because we interchange the role of electric and magnetic, the electron is now given by the same model that formerly we thought of as a monopole. In other words, that is what's called by geometers a metric on four-dimensional space, which is called the Taub-Nut metric. Forget about what the terminology is. It's a metric which has a lot of symmetry. It depends on a single parameter m, and if m is 0, you get the flat metric of R4. The symmetry is the same as the symmetry of C2 is U2, as U1 SU2. This parameter m, if it's not 0, it means that when you go to infinity, the space looks like a circle bundle of circle radius 1 over m. M gives the size of the asymptotic circle. And the charge minus 1 is, this notation, is the first Chern class at infinity of this one, and this is the standard model of the Hopf vibration. So the electron is, we knew it, we called it something else before, we called it a monopole, but why not change your mind? This is the electron. It's the simplest model there is of a manifold. This metric is a hypercalometric. One of the simplest examples, you can write it down, much studied, and so on. Now, the neutrino should be compact manifold, and neutrino is meant to be somehow partner to the electron. And so it should look very much like it, but it should be compact. Well, what partner is to R4 that is compact? The obvious answer is the force sphere. There's nothing. And because you want models, I should have explained, the basic models we want are ones which have spherical symmetry, because to physicists, a single particle, in space should be spherically symmetric. It doesn't distinguish between different directions. Protons, neutrons should all be spherically symmetric. Electrons should be spherically symmetric. And these are spherically symmetric. Now, you might think that the neutrino, if given by the force sphere, has even higher symmetry. That one might be a bit embarrassing, but I'll explain why. The symmetry is actually broken, something a bit smaller. See, the electron, thought of here is a four-manifold, and its boundary, the region of infinity, well, of course, in a real model, the mathematical model is something which is an asymptotic end. The real model will be chopped off at some length, and you'll think of manifold with boundary, and the boundary is glued into the rest of space. So if you're outside the electron, you see the boundary. Or you see the boundary in three space as the base of the vibration, a two-sphere, you see. This neutrino has no boundary. It's compact. So you might think you don't see it in space. It's somehow floating. Well, the only solution I can propose is that this neutrino actually intersects space-time in a two-sphere. And so what you see in space-time is the two-sphere, but the two-sphere doesn't bound something inside, it simply sticks out. In other words, this model here is one that's like an algebraic surface with two components. One is the basic space-time, or space, sorry, not time, four-dimensional space, and the other one is another four-dimensional manifold, and they intersect along a surface, like two algebraic surfaces intersect along a curve. Perfectly reasonable. Why should it all be one irreducible component? So this is the idea, and this intersection will take place along a two-sphere. This two-sphere in three-dimensional space, so the circle bundle over it is trivial. It's not like the two-sphere occurring there, where the circle bundle over it is the non-trivial vibration. Then you get the Hopf vibration, which gives you electric charge. Here, the bundle is trivial, and you can take any parallel two-sphere you like, and that will be where it intersects it. So the topology takes care of itself, and the distinction between compact and non-compact is fine, and the electric charge is handled, and that's all there is to it. Leptons are very simple. Now, the baryons are more interesting. Now, the first thing is, what is the neutron? Well, the neutron should be compact. It should be a self-dual manifold, and it should have SO3 symmetry. By the way, in the previous example of the neutrino, I told you the symmetry was broken down because once you fix the two-sphere in that four-sphere, then that reduces the symmetry. So in CP2, the complex vector plane, it has, of course, a lot of symmetry. It has a beautiful metric, famous Fabini's 2D metric, which is a self-dual metric with positive scalar curvature. And this CP2 should be representing the neutron. And like the neutrino, it's compact. Therefore, you should see it only in space where it intersects space in some surface. And my claim is that the surface where it intersects is, in fact, the real projective plane, thought of sitting inside the complex projective plane. And the reasons for that, which I can't explain in detail. Now, how do you find the real projective plane in ordinary space? Well, the answer is you don't. But if you blow a point in three-dimensional space, hey presto, you get the real projective plane as a blow-up. So start off with your original three-dimensional space, followed by circles over it. Blow up a point in the base space, lift the circle bundle up to it, and then you get the picture which fits this. So by a very simple bit of elementary geometry, you can arrange to have neutrons which intersect your space in real projective planes. And once you've broken the symmetry down to RB2, then the group that acts is, in fact, SO3. SO3 acting inside SU3, preserving the real structure, preserving the real plane, and that's the symmetry you've got. Now, the proton should be, having understood the neutron, we come to the last, the most difficult, in ways the most interesting model, the proton. The proton should be somewhat similar to the neutron, except it's non-compact. So the way to get that is to remove something from the neutron to make it non-compact. And what should you remove? Well, just remove this RB2, which before was where it intersected space. If you remove RB2 from CP2, you get a nice manifold, and it's known that there is a metric on this, which is a hyperkähler metric, and it's SO3 invariant. This metric was discovered by myself and Nigel Hitchin many years ago. That's our name. It's a beautiful metric. If you try to classify the self-dual solutions of the Einstein equations, which have SO3 symmetry, basically you find only 4 examples. The 4 examples are the 4 manifolds we've given. This is the most interesting one, because the solution of this one involves elliptic functions. It's not so trivial. The other ones are rather standard, well-known, easy, coming from group theory. This one involves something more difficult, and it comes from elliptic functions, and also some other facts about it in a moment. I should mention that when Nigel Hitchin and I first found this metric, by a lot of hard work, using twistor theory and so on, we published it, wrote it down. Somebody wrote to us and said, did you know this equation was the equation we got reduced to a single ordinary differential equation system was solved 100 years ago by a French mathematician called Halphen. And sure enough, we looked up his paper in the compte rendu, and it's one-page paper, and it says, consider the following differential equation. And he wrote down not Einstein's equation, he wrote down the one-dimensional equation that you get after you've imposed spherical symmetry on the self-dual Einstein equations. Heaven knows how he got the equation. He didn't say, I found this equation by looking at Einstein's equations. He couldn't have done. Einstein hadn't been born. How he got the equation is a mystery, but he wrote down the same equation and the same solution. So, it was done 100 years before, but our motivation was different. Now, 2 key facts about this example, which are very important. The second one, down the bottom, is that this metric has a circle action which is only an asymptotic circle action. In other words, it's not an exact symmetry of the manifold, it's only asymptotic symmetry. It gets better and better as you go further out, exponentially close. And the metric you get is like the metric we had on the electron, the tau-nut metric, except it has the wrong sign for the mass parameter. If you try to construct a solution of the tau-nut with the wrong sign, then you find that you can't do it. It gets singularities in the middle. But we don't take the exact asymptotic symmetry, we take only approximate symmetry, and then it exists, and inside the symmetry is not there, and inside this is the metric. And the fact that you get the wrong sign is why the proton has charge +1, and the electron has charge -1. So it fits very well. Now, the other interesting fact is here, and this is a fact which is a very elementary piece of geometry, which for a long time mystified me. I like this manifold because, I worked on it, and I kept thinking it's a very beautiful manifold we should use, and I kept thinking of it as a model for the proton, but somehow something seemed to be wrong, because the proton should have charge 1, and this RP2 inside here, it seemed to have all the wrong topology. You'd get the answer 2 or 4, or how can you get the answer 1? And finally I realized this very simple fact. The real projective plane, inside the complex projective plane, is, as you probably know, non-orientable. The complex projective plane is oriented, that's fine, but the real projective plane is not orientable. So it doesn't define an integral cycle inside the four-dimensional manifold. It defines a mod 2 cycle, that's fine, and easy to see that the self-intersection number of this mod 2 cycle is not 0, that's fine, but it doesn't define an integer cycle. Nevertheless, I claim it is possible to define the self-intersection number of non-orientable surfaces in an orientable four-manifold, so the answer is an integer. And if you do it in this case, you get the answer +1. The reason is that to define the self-intersection number of a surface, all you need to know is the topology in the neighborhood of the surface. In the neighborhood of the surface, you have fundamental group of order 2. So you can talk about homology with local coefficients. And the local coefficient system is also the same thing as the coefficient system of the normal bundle. And so you can easily see that there is a fundamental class in this twisted coefficient system. If you square it, you get to the ordinary coefficient system. So the square of this fundamental class is the self-intersection number, and that is interpreted as the electric charge in this model. And so you find that the real projective plane is self-intersection number +1 in CP2. You also see it by going to a branch covering and doing geometry directly. So this was a fact I found. I'm really very pleased when I got this answer, because finally, if you got +2, the theory would be thrown out of the window. Totally wrong, because the proton has to have charge 1, and it has the right sign and everything, and the right topology, the right symmetries, but if you didn't get 1, it would be a disaster. Fortunately, I got 1. Sometimes you don't believe these things, I checked it and checked it and checked it several times. Every time I explained it to somebody, they say it must be wrong. Now, some comments. First comment is that when I said that this four-dimensional manifold, the metric CP2 minus RP2, had a circle fibration at infinity asymptotically, I didn't point out the circle fibration is by unoriented circles. That's a reflection of the fact that RP2 is not oriented. It's the normal bundle of RP2 in CP2. And so, if you quotient down by that circle, the three-dimensional space you get, which is meant to be our ordinary space, is not orientable, not locally orientable, around the point where the proton is supposed to be, you have a non-orientable three-manifold. Well, you have to live with that. It means the double covering is orientable. It's the quotient of an orientable three-manifold by reflection in the origin. You might think that having a lack of orientation was a disaster, but in fact, it's not such a disaster, because when you go around in the fundamental group and change your orientation, you also at the same time interchange the sign of the circle, which measures the electric charge. So if the only thing you're ever using is electromagnetism, you won't notice it. In other words, the orientation, the electric orientation is still preserved. The geometric orientation is not, but it's not that one you're worried about. It's the physics. So this is not a serious problem. If you look at the more general models, for charged leptons of higher numbers, then the general situation is likely to be that for the leptons, you get singularities of what are called AK type, corresponding to the Dynkin diagrams SUN, and for the baryons, you get those of DK type, corresponding to the even orthogonal groups, in which the change of the fork of the two ends of the Dynkin diagram corresponds to the change of orientation of the circle. So this fits quite well with what we know about geometry of singular manifolds and so on. No, there's lots more problems. If we got this far, I've got some models, theoretical ideas how to develop it, gluing together. But you see, it's just the beginning start of a program which is a long way to go. Here's some more comments. These two spheres of the real projective planes that arose in this picture have natural geometrical scales, and they might relate to the masses of the various fundamental particles. Secondly, I remind you that in a four-dimensional manifold, you have two SU2s. And when you have a hyperkähler manifold, one of these SU2s is killed off, it's trivialized. And this might be related to what's called isospin for physicists. Isospin is a phenomenon, well, it's an approximate symmetry in nature in which you treat the proton and the neutron as a doublet pair. You ignore the fact that they're different, slightly different mass, and that one is charged and the other is not. And if you ignore those facts, you see an SU2 symmetry. It's called isospin, because spin is the real symmetry, isospin is fake symmetry. And in my geometrical model, the neutron is given by a self-dual, but as a positive scalar curvature, so it's like a Kähler manifold, but not a hyperkähler manifold. And so the two are quite closely linked, as close as you'd get from a point of view of isospin. So it may be that the isospin idea can be explained in this model. And lastly, if you have a manifold with a metric on it and so on, then of course we would want to study the Dirac operator on it, look at its spectrum, and relate that to the physics, spectral properties of physics. So that's again a program for the future. Let me finally finish with another quotation by Dirac. He's one of my favorite authors of quotation, the other being Einstein. But here what he says is the same article that I wrote before. He says, he was talking about the possibility of mathematics and physics coming together. He says, at present, that's 1939, we are, of course, very far from this stage, even with regard to some of the most elementary questions. For example, only four-dimensional space is of importance in physics. He was wrong there, but while spaces with other numbers of dimensions are of about equal interest in mathematics. It may well be, however, this discrepancy is due to the incompleteness of present-day knowledge, and that future developments will show that four-dimensional space will be of far greater mathematical interest than all the others. Well, that's a prediction of Donaldson theory, a long way ahead of his time. So it's a very remarkable remark of Dirac, who shows that he was thinking a long way ahead, and you should go back and read what he said. It's an indication of where we might be going. Well, sorry I've gone on a bit too long, but I was trying to cover the whole of physics in a small form, so I needed a few extra minutes. Thank you.